The second video in this chapter looks at how constraints affect optimization. So we've established in the previous video that including constraint information systematically into a control design is important, and now we want to ask ourselves, how can we actually do this? Predictive control is based on the optimization of predicted performance with respect to some predefined degrees of freedom within the predictions. So in principle, it should be straightforward to add constraints to any such optimization. What we're going to do in this video is look at how we can incorporate constraints into a QP optimization, because that's the structure of a typical predictive control law. The early videos demonstrated that a typical MPC performance index has a quadratic dependence on the degrees of freedom. Now, a typical quadratic can be expressed as something like this. You'll see we've got J equals X transpose Sx plus X transpose B plus C, where S is greater than 0 or positive definite, and in particular we also know that S equals S transposed. Now, the optimization or the minimization of this A with respect to the degrees of freedom in X has a solution something like this, which we've covered in earlier videos, but critically this is the unconstrained solution. Okay, so that's what we've covered earlier. If we do an unconstrained solution, then the answer is unique and we can write it down. Let's illustrate what these J's look like then. So what I'm going to do is plot some contours of J in X space, and I'm going to use 2 degrees of freedom to keep it simple, so you can get a visual impression of how J changes when I change X. So here's the J that I'm going to use, just some arbitrary numbers, and here is a plot of how J changes. So if you imagine this axis here, for example, was X1, and this axis over here was X2, then what you can see is clearly the best place to be is down at the bottom of this bowl, and that's where the optimum will be, and that's where the gradient is 0. And as you move away from the bottom of the bowl, clearly J increases. Now, it's easier actually to do a contour plot. So that's what I've done here. I'll just get rid of those so they don't distract us. So I've done a contour plot using the X1 axis and the X2 axis, and it's fairly clear that the optimum point is at the center of this contour plot. What we're going to do next then? We're going to add some constraints into this problem. So what happens to the minimum value of J if we insist that some constraints are met? So again, you'll notice we've given the contour plots of J, and the place where we'd really like to be, if we can, is this center point, because that's where J is as small as possible. But what I'm going to do now is add a constraint that X has to be bigger than 1.5. Or I should say X1 has to be bigger than 1.5, but this is the X-axis down here. So if I add to that constraint, there's that line, and what I'm saying is essentially I have to be over here. And it's fairly clear that now I cannot access the unconstrained optimum. And the best I can be is where this green spot is. And the reason I know that's the best is because it's the smallest ellipse, okay, within my allowable space, and therefore it's the smallest J. Next, I'm going to add an additional constraint that X plus Y is bigger than 1.5. So let's imagine that's the Y-axis, and there's this line here. So now I also need to be above this line, and fairly clearly the optimum point is now where that red dot is, and you can see J has got bigger again. So I'm just going to make this up. If that circle or ellipse was, for example, J equals 1, this one might be J equals 2, this one might be J equals 3. I know they're not exactly those values, but it's indicative. You can see that as I introduce more constraints, the size of J is getting bigger and bigger. Let's add another constraint now. So I'm going to add X plus 0.2Y is bigger than 1, and that's that line here. Now that's telling me I've got to be above this line, and you can see that has no impact on my optimum, because the optimum I've got already meets that constraint. So sometimes you'll have constraints which are what we call redundant. They do not affect the optimum, and other times they do. So here's an example of a sort of mathematical representation of the problem we've just done. You'll see we've written the quadratic part at the top, there's my j, and we've represented the constraints using inequalities like this. What we noted was that for this case, the top two constraints influenced the optimum solution, but the third constraint was redundant. Now, let's look at some different examples. In this example here, you'll see I've got three constraints. The constraints are given by these dotted lines here, and what I'm looking for is where is the constrained optimum. Now clearly, in order to meet all of these constraints simultaneously, I'm going to end up somewhere like this. Okay, so my optimum is actually based solely on this constraint. You'll see the other two constraints are redundant in this particular case. Now a constraint is active if its inclusion affects the constrained optimum. So in this case, only one constraint is active. Now a constraint is inactive or redundant if its inclusion does not affect the optimum. Now here's the key thing: the constraints which are active will depend upon the position of the unconstrained optimum, that's this bit here, and also of course on the shape of these contours. So what I've done here is I've moved the centre. You'll see the centre is now moved to here, and if I now ask myself where is the unconstrained optimum, in this particular case you're going to come up with it somewhere around here. So you'll see now different constraints are active to before and different constraints are redundant. The number of active constraints in this particular case could be 1 or 2, because the constrained optimum could be on a side or it could be on a corner. Now using MATLAB to solve these sorts of problems, the optimization discussed here is a quadratic program. This has a quadratic performance index and linear constraints, and typical notation is something like this. You'll see we minimize x transposed sx plus x transposed b plus c subject to mx less than or equal to d. Typically when you're using MATLAB, it prefers if you put a half on the quadratic part of the performance index, so you just need to bear that in mind when you're doing your MATLAB coding. The program that MATLAB provide for you is called quadprog, and you'll notice you put in your S matrix, which is taken from there, you put in your B vector, which is taken from there, you put in your M, taken from there, and your D, taken from there. Now there are also several other options within quadprog. I'm not going to go through those. I suggest you go help quadprog to understand what they are. Here's an example then of using quadprog, and you'll see it's in the file, sorry that didn't work, video 5_2_ example1.m. So I'll just show you these files briefly, but I'm not going to run them. But you'll notice we've got a 5.2 example 1, a 5.2 example 2, and a 5.2 example 3. What do? They define a B, and you see there's different B's here you can try. They define a C, an S, an M, and a D. Now obviously you can change these should you want. The files should work. You'll notice we define the unconstrained optimum here, and we then use quadprog to find the constrained optimum, and then the bottom part of the file is the bit that generates these contour plots. So it's got these loops, it's a bit tedious, but that's where you get the contour plots from. So I'm not going to run those, but you can easily look at them and modify them should you want to. So here, in this particular case, you can see what that file has produced. It's produced the unconstrained optimum, there it is. It's produced the contour plots, it's produced the inequalities, and it's told me that the constrained optimum is here. If I change the value of b, so you'll notice it's the same example because at the top there is different values of b you can choose. When I change b, the centre, or the unconstrained optimal, changes, and so the constrained optimal has changed. And there's another example. In this particular case, you can see that the unconstrained optimal satisfies constraints. And because the unconstrained optimal satisfies constraints, then the constrained is the same as the unconstrained. And that's another example here. You can see the unconstrained optimal is all the way down, somewhere down here. and this is where the constrained optimal will be. What about example 2? This has got a slightly different shape on S. You'll notice the ellipsoids now have this sort of orientation, but other than that, it's simply showing different examples, different illustrations. So I'm not going to dwell on those. You can look at those slowly in your own time. You can go to these M files, you can change the B's, and you can run them. Now, obvious point, the similar insights will carry over to higher dimensional cases where you have 3 degrees of freedom, 4 degrees of freedom and so on, but it's quite hard to illustrate those in figures, which is why I am not doing that. Now this example here, however, is quite important, and you'll notice I've put in the title Counterintuitive Results, because this is what you really need to know if you're going to look at predictive control, and this is in example 3. Now what I've done here is I've given you what look like box constraints. So you can imagine this as being something like u under bar less than u over bar, and that could be uk, and you could have u under bar less than uk plus 1 less than u over bar. So it could be simple upper and lower limits on an input, and your input could be your degree of freedom. So basically it says that your optimum input has to lie inside this box. Now the unconstrained optimum is given down here. It's clearly nowhere near your box, you can't implement it. So you want to say what's the best position in the box with regard to my cost, and here's the interesting point. Your unconstrained optimal is somewhere around 1.8. Where is your constrained optimal? It's somewhere like -1. And here I'm looking at the UK axis, which is this bottom axis. So what's rather worrying here? Your unconstrained is above the upper limit, but your constrained is actually on the lower limit, and hopefully you can see why that's quite shocking, because what it's saying is if you use saturation control, then you would have used UK equals 1. That's what saturation control would give you, but actually the optimum, when you take constraints into account, is UK equals -1. It's counterintuitive. It basically says move the input in totally the opposite direction to where you might expect. And this tells you why sometimes including constraints is critical, because if you include constraints, then the best choice of your input trajectory could be totally different to what's best if there are no constraints. Okay, so the summary there is that saturation control could be very poor indeed. It won't always be, but there are cases where it will be. So a summary: a failure to take proper account of constraints during a feedback design can have several undesirable consequences. This video has introduced the quadratic programming optimization, and it's demonstrated that the inclusion of linear constraints changes the optimum. That's the key thing. The optimum is different. You can't just do saturation. And we've illustrated how the insights from these constrained optimizations show that the best strategy can be, and I've emphasized here not must be, but just can be, far away from a saturation policy. And that's why it's important that you actually do it properly, because a priori you won't know when saturation is good and when it's bad.